So that takes us to linguistics. How can we understand each other? How in the world can, when I say the word howdy, that sounds different than you saying howdy. So how in the world do our brains understand each other talking if we're producing different sounds? Okay? That's, this picture over here on the left represents what's called a two-tube model for the way that sound is produced by the human throat. So the idea is that you have a throat here, and the way that my lips and my tongue are shaped influences the sound that comes out. For example, father, fa, that vowel sound, my mouth is wide open. Father, teeth, teeth, my lips are it's a much different position of my throat, of my tongue and my lips. Turns out that I basically can, well, I don't. Somebody else has solved the differential equation that governs how air would flow through a two-tube model, and to figure out, why sound comes out the way it does. There's a boundary condition that has to occur at the interface. That basically the boundary between where your throat ends and where your mouth starts. And solving that differential equation gives a certain boundary condition, which is given by the equation on the top. That top equation determines the frequencies that are most promoted by your voice when you shape your shape your vocal tract a certain way. So father, my mouth is wide open, so my area of my mouth, A sub m, is going to be much larger. Okay. Also, the length of my mouth is going to be much larger because my teeth are wide open. Okay. Solving that equation, setting that equal to 0, and basically graphing the thing and seeing where the x-intercepts are, gives us a way of figuring out what frequencies are most promoted by the vocal tract. In this case, it's about 800 hertz and then about 12 or 1300 hertz. And those two frequencies are going to be roughly the same for most adult men that are saying the vowel sound ah. So even if I talk differently than a different man, the overtones, the frequencies that are most promoted by the vocal tract, are going to be those two same frequencies. So we can understand each other even though we don't sound exactly the same. Wonder how the brain works. What you see here is your typical two-format chart that determines pretty much how vowel sounds sound. I invite you to do this quietly in your seat. Hood, hood, hod, hud, hod. And just feel how your mouth is a little bit different shaped as you go from left to right. As you go from left to right, the different formants are going to change because of the shape of your vocal tract, and so the different vowel sounds get produced. Going upwards, so heed and hid. Heed, hid. Your mouth is just a little bit more open for hid than heed, and hence the slight difference in how it sounds. Okay, so this takes us to voice recognition. What you see on the right is a synthesized vowel sound. What is it? What's he saying? This is basically the problem that voice recognition software works. When you call American Airlines and make your reservations on the phone, and you want to end up in Tahiti and not in Pilot Point, they want to make sure that the computer needs to recognize the words that you're saying so that it can identify where you're going. Okay, the principles behind this are basically from Fourier Analysis. And the principles of Fourier Analysis is basically something that can be done in Calculus 1, at least the basic ideas behind it. Here's the idea. The idea behind Fourier Analysis is based on a couple of integrals. First integral goes like this. Sine of m pi t over capital T times sine of n pi t over capital T. So two different variables here, m and n, dt, integrated over one period. Okay. Now this is another trig identity that everybody forgot. If I have the product of two trig functions, there's a trig identity that changes that into the difference, in this case, of two cosine functions. Okay? So the product of these two sine functions can be written using this trig identity in terms of the difference of two cosines. So this product of sine functions cannot be integrated directly. But I can use a trig identity to change it to something that I can integrate. Integral of cosine is sine for both of these. So when I integrate, I get a sine and a sine. Now integrate from evaluate from t to 0. All right. When I plug in 0, sine of 0 is 0. Okay, that's good news. When I plug in capital T, if I put a capital T here, that cancels the capital T down here. So that leaves me sine of a positive integer times pi. Sine of any integer times pi is 0. And so this integral is 0. Henceforth, if I ever see sine of m pi t over capital T, sine of n pi t over capital T, integrated from 0 to t, as long as that m and n are different, that thing is 0. And I don't have to worry about it. What happens if they're the same? If m and n are the same, then I have sine squared. So let's talk about what happens if I have sine squared. Well, there's another trig identity, long since forgotten by pre-cal students, that says sine squared theta is 1 minus cosine 2 theta. So I integrate this. Integral of cosine is sine, and that once again goes away and becomes 0. But I have this extra 1 over here. The integral of 1 over 2 is t over 2. And when I plug in capital T and 0, I now have something that is not 0. I get one thing here that is not 0. Okay, so the moral of the story. If these numbers here are different, then this integral turns out to be 0. If they're the same, then I get a non-zero contribution t over 2. Okay, so let's pretend that this is our sine wave, this Fourier series, adding a bunch of sine waves together. Okay, then if I try to integrate, if I multiply by a sine wave and integrate, then nearly all of these terms here are going to go away because m and n are different. The only term that survives is the one term where m is actually equal to n. So if m is equal to n, then that one term survives, sine squared. Otherwise, they all go away and you get 0. And the one term that survives, you get t over 2, like we just saw. So the net practical effect is that the coefficient of a sub n is equal to this integral times 2 over t. So if I want to figure out what frequencies are being promoted, I just have to integrate the function here. This is called a Fourier Transform. This is the basic principles behind the real Fourier Transform. It's simplified for the language of calculus students, but that's basically the idea of how a Fourier Transform works. All right, so given this question, what's the guy saying? If I numerically compute this integral, using Simpson's rule or trapezoid rule or whatever, if I numerically compute this integral, I can figure out what frequencies are being set. So in this case, that's the spectrograph that occurs. We have frequencies at 200, 400, 600, so on hertz, multiples of 200. And this is what typically happens by one voice. The multiples that come out are going to be multiples of a certain base frequency. But you see the peaks here. The first peak occurs at 400. The next peak occurs at about 1400. And so looking at my chart, that occurs there in the chart, 400, 1400. And so we think that that sound is going to be a schwa vowel, heard, or one of the schwa vowels. Not bad by doing a bunch of integration.
The what vowel?
Schwa.
What are those?
That's when you're not, the most typical is the, where your mouth is pretty much at rest and just let sound come out of it. That's when your mouth is at rest, you're not trying to promote any particular sound. It's called the schwa vowel. S-C-H-U-W-A.